Next, we're going to look about graphing on the calculator. Sometimes I want you to graph by hand and other times by the calculator. The more complicated graphs we will do by the calculator. So you write the equation with x representing the independent variable and y the dependent variable and solve it for y. So we want it in the form y equals always. Enter the function in the equation editor of the graphing utility. Use parentheses when needed to ensure correctness of the expression. Activate the graph by pressing the zoom or graph key. Most graphing calculators set viewing windows under zoom, and including the standard viewing window that gives the graph of the function with the coordinates x values ranging from -10 to 10 and y values from -10 to 10. To see parts of the graph other than what's shown in the standard viewing window, you press Window, set the x and y boundaries you need for the viewing, and then press Graph. The viewing window values are discussed below and in the technology supplement. That's below in the textbook where this appears in the textbook. And there is a technology supplement in your at the back of your textbook also that can help you with these things. So here's our equation. We've got it in y equals form. Y equals x cubed minus 4x squared minus 15. We're going to sketch the graph in the standard viewing window first. So that's with x values from -10 to 10 and y values from -10 to 10. And I'll show you how to do that. And then we're going to do the same equation. We're going to change the viewing window. So we'll go from -10 to 10 for the x values, and the y values will use -25 to 10. And then they ask which graphs gives a better view of the graph for the function. To graph on your calculator, we'll start by going to y equals. And we're putting in the equation x, you'll find x here, raised to the third power, and use the right arrow to come down, minus 4x, and there is a squared button, minus 15. That's our equation. They ask us to do it on the standard window first, so the standard window is from -10 to 10 for the x values and -10 to 10 for the y values. And then we'll go to graph. And this shows the graph. Doesn't look like a very complete graph. They ask us to change the window. And x values from -10 to 10 and y values come down here to the y values, and this is the -25. And let's graph that. Oh, much different graph. This one looks like it could be our better one. So here are both graphs on the same, so we can see both graphs at the same time. Notice that our graphing calculator does not number these, so we have to go back to the window to find out what those are. We know we did from -10 to 10 on both the x and y axis. This one, x-axis was -10 to 10, and this was -25 on the y-axis to 10. Sometimes I will ask you to prove that you did it to draw a sketch of your graph. I would like you to show me where your axes are, number what your window was, and then make a sketch of it. So here's our two windows, the standard window, and changing the y values to -25 to 10. They ask which graphs gives a better view of the graph of the function. And I would say that the second window does, because this graph has two turning points and we can see them both here. On the first graph, we can only see where it crosses the x-axis. We don't have where it crosses the y-axis. So the second one is the better window. And sometimes you will have to experiment and just change the windows to see what gives you the best view. Now, we'll have an actual application. Suppose the cost C of removing some percent of the pollution from drinking water is given by this model. Using the restriction on P to determine the limitations on the horizontal axis values. Well, looking at the restriction on P, we have 100 minus P in the denominator. If that equals 0, then it turns out that 100 would equal P. So we have a restriction. We can't go below 0% or greater than 100%. In fact, we can't even have it equal 100%. So we can use a window from 0 to 100. So they ask us to graph this function in the viewing window from 0 to 100 for the x values and from 0 to 50,000 for the y values. Why is this reasonable to graph this model using this with the limitation that C is greater than or equal to 0? Well, the cost is probably never going to be less than 0. And find the point on the graph that corresponds to, we can pick different values, and I think we'll do a couple of them and talk about what those mean. To graph this function, 4950 x in place of the p divided by, since this is the denominator and it has more than one term, we'll put parentheses around it, 100 minus our x, and make sure you close the parentheses. They ask us to do this window from 0 down to 100 and continuing on down from 0 to 50,000. And this would be our graph. Let's say we want to find a value for p equals. So do that as second calc, and we want to find the value when p equals. So we select enter, and let's have p equal 50 and remove 50% of the pollution. We'll find it's 50 and 4,950. We can find a different value. P equals, maybe we want to remove 75% of the solution, of the pollution. So 75, enter. Now it costs $14,850. We could do that for a variety of different things. So here we have our completed graphs, our graph, and then we have for x equals 50, we come out with 4,950. That means to remove 50% of the solution, 50% of the pollution costs $4,950. Here are 75% to remove 75% of the pollution from the drinking water. Will cost $14,850. And I don't know about you, but I'd really like that to be close to 100%. Well, we can see it's going up, and 100% was the end of our X scale. See how it's going up beyond. This is the top of the Y values at $50,000, and we have gone above that.